Okay, this video is about how to predict which would have the higher melting point by just looking at the intermolecular forces in substances. Okay, so the first one is CO2 versus H2O. And so the first thing that you need to do is identify the types of forces in each. And so probably, unless you know, you have to draw the Lewis structure. So if I have CO2, I'm going to draw that. And I'm going to find out that it's linear and the dipoles cancel each other out. Therefore, it's nonpolar. So the only forces that it has would be London dispersion forces. Okay, now water, if you draw that, it's going to be bent. That makes it polar. And because it's polar, okay, another water molecule could be attracted. So it has a special type of dipole-dipole interaction right here. That's called a hydrogen bond. Now, water also has London dispersion forces. Everything has London dispersion forces. Now, CO2 has slightly more London dispersion forces because it has more electrons, but the hydrogen bonding is much stronger than this. The only attraction that a CO2 would have for another CO2 would be, the London dispersion forces between it, the only attraction. Okay, so I think the hydrogen bonding here is going to trump the London dispersion forces in the CO2. So water would probably have the higher, well, it does have the higher melting point. And you know this, if you ever take carbon dioxide and you put it in a regular freezer, it all goes away. I kind of learned that my lesson the hard way before I knew a lot about chemistry, I guess, is I bought some once and put it in a freezer and I opened it up and all the CO2 had sublimed and turned into a gas and the bag that it was in was empty. So anyway, all right, let's try another one. So here we have NaF and HF. All right, so if you look at the forces, well, NaF is ionic. So you have a sodium ion that's going to be attracted to a fluoride ion with an ionic bond. So this is an ionic bond that holds those two together. Whereas HF is a molecular compound, okay, nonmetal to nonmetal. Now the HF is held together with what would be called a hydrogen bond because it makes a hydrogen sandwich between two fluorines. So this one has hydrogen bonding in it and it has dispersion forces, and I like to abbreviate them LDFs, London dispersion forces. You don't need the apostrophe. LDFS, London dispersion forces. Okay, but this ionic compound, an ionic bond, is much stronger than hydrogen bonding. Okay, and also this one also has London dispersion forces. So the ionic bonding and the London dispersion forces in NaF and NaF would be a lot stronger force of attraction than HF because when you go to melt something, you have to break this bond apart. And so the ionic bond is much harder to break apart, therefore it has the higher melting point. Okay, F2 and HBr. So you would draw F2 and it would be a molecule like that. And so it's a non-polar molecule, so it only has London dispersion forces. So the only attraction that F2 would have for another F2, there'd be a very weak attraction. That would be a London dispersion force. Okay, now HBr, if you drew HBr, these two have a difference in electronegativity, so it's going to be a polar molecule. So one HBr could attract another HBr, and there would be an attraction right there. Now, it doesn't have hydrogen bonding because there's no hydrogen sandwich between FO and N. That doesn't happen here. So there's no hydrogen bonding. So it's just a dipole-dipole interaction. A polar molecule attracting to another polar molecule. Okay, this one also has London dispersion forces. Everything has dispersion forces. Okay, and it's based on the number of electrons. So if you're comparing this one, the dipole and the London dispersion forces would be stronger than just the London dispersion forces here. So HBr would have the higher melting point. It would take much more energy to break this attraction apart versus breaking this attraction. Okay, NH3 and BH3. So you draw NH3, and NH3 you would find is trigonal pyramidal, whereas BH3, remember boron is the one that, H there, boron is the one that violates the octet rule. Okay, so this one is non-polar, this one is polar. Okay, so now this one is non-polar, so it only has London dispersion forces. Okay, this one also has London dispersion forces, but this one, this is called ammonia, it can hydrogen bond with itself right here. So this nitrogen end right here would be attracted to the hydrogen end. Okay, and that's going to make a hydrogen bond. Notice that the nitrogen, hydrogen, nitrogen. It makes a sandwich between F, O, or N, but in this case it's two N's, a hydrogen sandwich. That's a hydrogen bond. Whereas this one, another BH3, would only be attracted to another BH3 through London dispersion forces. That would be the only attraction. Because the hydrogen bond and the London dispersion forces in NH3 would be greater than just these London dispersion forces in BH3, NH3 would have the higher melting point. Okay, CH3OH. So if you were to draw this, you would get CH3, this is called methanol, OH, and there'd be a lone pair there, a lone pair there. C2H6, so this is ethane. Okay, it's going to look like that. Now this molecule is symmetrical, and anyway, it's going to be nonpolar. This molecule is not symmetrical, it's going to be polar. In fact, this CH3OH, it can hydrogen bond with another, although it would hydrogen bond right there. Then you'd have carbon, hydrogen, hydrogen, hydrogen. It would hydrogen bond with itself right there. Okay, and it could also hydrogen bond here and on the other side of that oxygen. But anyway, this one is polar. It has London dispersion forces. Okay, but it can also hydrogen bond. C2H6, on the other hand, it only has hydrogen, or no. It only has London dispersion forces because it's nonpolar. So hydrogen bonding along with the London dispersion forces in CH3OH would be greater than the C2H6. So this C3OH would have a higher melting point than the C2H6. Okay, CH4 and CL4. So if you draw them, you'll see that they're both tetrahedral and they're both symmetrical. Okay, and because of that, they're both nonpolar. So when they're both nonpolar, they both have just London dispersion forces. Okay, that's all they each have. But if you look, the CL4 has more electrons, and more electrons makes what's called a greater polarizability, if that's even a word. I think it is because I've heard it before. It has a greater polarizability, and so therefore the more electrons, greater polarizability, that's going to give it a higher melting point. So if you're comparing things with just London dispersion forces, the one with more electrons will have the higher melting point. So that's CCl4. Okay, that's it for this video, so I hope that helps you out.